All right, welcome. Today we're going to dive into a brilliantly simple algorithm that's working away completely behind the scenes of your digital life. It helps with everything from medical diagnoses to, and this is its most famous use, filtering all that spam from your email. It's called Naive Bayes, and we're going to get a real feel for how this thing actually works, step by logical step. Right? Just picture your inbox for a second. It's a relentless flood of information, isn't it? You got messages from your boss, updates from your friends, and then all the rest. That endless stream of offers, alerts, and just absolute rubbish. Keeping the important stuff separate from the junk is a huge challenge, right? So how on earth does your email service get so good at sorting the wheat from the chaff all on its own? How can a bit of code just read a message and make a surprisingly good guess on whether you actually need to see it? Okay, let's dive into this. So it all kicks off with learning from examples. I mean, you can't just tell a machine to look for spammy words. You have to literally show it what spam looks like and what normal emails look like. This whole process is called training, and it starts with data we already have. Basically, two big piles of messages we've already sorted ourselves. One marked normal and the other spam. Let's start with the good pile then, emails from people we actually know. The algorithm's first job is to read through all of them and just count. It builds a sort of frequency table, a histogram, tallying up every single word. How many times does the word dear pop up? What about friend or lunch? It's basically creating a statistical fingerprint of our normal chats. Okay, so we've got these raw counts, but here's where it gets clever. We turn those counts into something way more useful. Probabilities. So if dear showed up 8 times in a collection of 17 words from our normal emails, we can figure out the probability of seeing dear given that we're looking at a normal message. And the maths is actually pretty simple. 8 divided by 17 gives us 0.47. And we do this for every single word. Right, once we've got the profile for our normal mail, it's time to, rinse and repeat for the junk pile. So the algorithm just gets to work chugging through every single spam message, and again, just counting up how often each word appears. This builds a second, totally separate vocabulary, a profile of what spam tends to look like, based on our own data. And here we go. This is the result of all that work. On the left, we've got the word probabilities for our normal messages. You can see dear and friend are fairly common. But have a look at the right-hand side, the spam profile. The probability of seeing the word money is huge, 0.57. That's compared to a tiny 0.06 in our normal emails. The machine has learned a vital clue. All right, training complete. Our algorithm now has its two different worldviews, its idea of normal language versus spammy language. It's ready. A brand new, unseen email hits the server. Now, it's decision time. So, let's throw a simple test case at it. The new email just says, Dear Friend. Now the algorithm has seen both of those words before during training, but not necessarily together like this. Its job is to calculate a normal score and a spam score for this specific message, and then it's just a case of seeing which score comes out on top. But hold on a sec. Before we even look at the words dear and friend, the algorithm needs a starting point, a kind of baseline assumption. Like if you knew nothing else about an email, would you guess it's normal or spam? This baseline is a really important idea called the prior probability. So think of it like this. The prior probability is what we believe before we've even seen the evidence. In our training data, we had 8 normal messages out of a total of 12, so our prior belief is that any random email has an 8 in 12 chance, or about a 0.67 probability, of being normal. It's our initial bias based purely on what we've seen in the past. Okay, now we can combine that baseline guess with the evidence from the message itself. To get the normal score, we take our prior of 0.67 and we multiply it by the probability of seeing dear in a normal message, which we already know is 0.47. And then we multiply that by the probability of seeing friend in a normal message, which is 0.29. And when you crunch those numbers, we get our final score. So this is the crucial bit, 0.09. You can think of this number as a kind of measure of belief, a confidence score that this message, dear friend, belongs in the normal pile. Right, but one score isn't enough, is it? We have to do the exact same calculation, but this time for the spam category. So we take the spam prior, multiply it by the spam probability for dear, and the spam probability for friend. That gives us a much lower score, just 0.01. The final decision is now incredibly simple. 0.09 is obviously bigger than 0.01, so the algorithm confidently decides the message is normal. And that's it. Okay, that all seems pretty straightforward, right? But reality is always a bit messier. What happens when the algorithm stumbles upon a word it's never ever seen before in one of the categories? Let's see how we can build a much more resilient system. Check out this new message. Lunch money, 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 money. I mean, our gut feeling just screams spam. But there's a massive problem. In our training data, the word lunch only ever appeared in normal emails. That means its probability of appearing in spam is 0. And in maths, when you multiply anything by 0, well, the whole thing just becomes 0. Poof, the entire spam score is instantly wiped out no matter how many times money appears. And that right there, that's called the zero frequency problem, and it's a classic way to break a classifier. A single new word can bring the whole system crashing down. Thankfully, there's an incredibly elegant fix for this, a simple but really powerful technique known as smoothing. So how do we fix it? Well, here's how it works. We go back to our original frequency tables and we add 1 to the count of every single word, even words that never actually appeared. This little value we add is called alpha. It's kind of like we're pretending we've seen every word in the dictionary at least once. This simple trick makes sure that no word's probability can ever be absolute 0. And what happens when we apply this smoothing? Well, suddenly, the probability of seeing the word lunch in a spam message is no longer that catastrophic 0. Instead, it becomes a very small, but crucially, a non-zero number. In this case, 0.09. The calculation is safe from breaking, and the algorithm can now make a proper judgment. And would you look at that? With smoothing in place, check out the final scores. The normal score is absolutely minuscule, but the spam score, while still small, is over 100 times larger. The algorithm compares them, and that message, lunch money, 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 is now correctly flagged as spam. The system is fixed. Okay, we're almost there. But we have to talk about the name. Why on earth is it called naive Bayes? What's so naive about it? Answering this question really gets to the very heart of why this approach is so fast and, against all odds, so effective. Right, it's called naive because it makes this one huge simplifying assumption that, if we're being honest, is just wrong. It assumes that every single word in an email is completely independent of every other word. It basically treats a message as just a bag of words, where order, grammar, and context are completely ignored. For this algorithm, dear friend gets the exact same score as friend dear. Now, we all know that in human language, word order is everything. Man bites dog is very different from dog bites man. But here's the crazy thing. That naive assumption, that's its superpower. As the quote says, trying to keep track of all the complex relationships between words would be a computational nightmare. By just ignoring all that complexity, naive Bayes stays lightning fast. And that kind of brings us to a final thought, doesn't it? This algorithm is simple, and it's built on an assumption about language that we know isn't really true, and yet it works remarkably well for so many things. So it really makes you wonder, if something so naive is this effective, just how much of our digital world is quietly running on this principle of making fast, good enough decisions for us every single day.